Hi everyone. So I'm very glad to be here to talk about two systems that we have been building over the last couple of years. The first one is called Deep Dive, and the second one is called Caffe Control. For both of the systems, they are already available and open source, and you can play with it. And in the end of this talk, I will also talk about one of our ongoing fusion effort to try to fuse these two systems into a unified framework. Let's start from the system that we have been building called Deep Dive. Deep Dive is a system we built to support the workload that we call knowledge-based construction. I will talk about this workload later in details, but for now, you can think about it as a system that takes as input unstructured document and output a relational database that can be supported from the input. For example, given a text snippet like this, Deep Dive can extract relationship between rock formations and their location and age, and store them in a relational database. For those of you that are familiar with database research, this task is very similar to information extraction task. And for those of you who are very interested in machine learning and natural language processing, this might sound like a relation extraction task. Deep Dive learns a lot from these two communities, and on the other hand, tries to extend this ability to more diverse sources of resources. For example, tables, document layout, and even figures. In this talk, I will talk about the Deep Dive framework and how it makes all these tasks easier. The focus of Deep Dive to support a diverse set of input requires it to has the ability to take as input a diverse set of resources. And in this talk, I will first talk about the Deep Dive framework, and then a deep learning engine that we have been building called Caffe Control, and then our ongoing fusion to fuse these two pieces together. Over the last couple of years, we have been chatting with a lot of scientists and our collaborators, and one thing that we learned from them is nowadays many pressing scientific questions are microscopic. What does this mean? It means that to get an answer or hint to many questions, we need to aggregate a larger amount of facts and draw insight from them. Let's take paleontology as an example. When scientists want to understand the questions, like what is the impact of climate change to biodiversity, one way to get some insight is to start from a collection of facts about what fossil appears in what rock formation. And they also need the age and location of a rock formation. Given this collection of facts, they can aggregate them together to get what we call a biodiversity curve, which essentially tells us at a given time how many distinct species are there on the planet. From this microscopic view, geoscientists can get some insight to help them to understand these scientific questions, like the one about climate change. We can see that if we want to support this workflow from scientific fact to scientific insight, we first need to have this collection of facts ready for analysis. Ideally, we want this information to be stored in a relational database and can use existing query tools to analyze them. However, in practice, many of these facts are not currently stored in a relational database. And if you look at the paleontology, many of these facts are published in journal articles or books that could be more than 400 years old. In this talk, we call this collection of scientific facts organized in structured form a knowledge base, and the process of extracting this knowledge base construction. As we can see here, this KBC step could provide one possible starting point for scientists to answer key scientific questions. This example workload not only appears for paleontology. Now, in our past experience, we found that a similar KBC process could be useful for a whole range of domains. For example, for genomics, if we could build a knowledge base between gene, drug, and diseases, we could help the patient to get a personalized medical plan. If we can extract from the web about the communication between bad guys, we might be able to help to make this world a better place. Now that we have seen that KBC is a potentially helpful process, then a natural question to ask is, can we just do KBC manually? Let's still use our paleontology example. Actually, building a knowledge base for this domain is so important that even before we have the support to do that automatically, people are doing that manually. It was like 30 years ago. There's a very famous geoscientist called Szymanski. He manually compiled a knowledge base that contains more than 3,000 of animal families by reading facts from like 400 different references. This monograph alone has been cited hundreds of times and lead to many important scientific discoveries. The importance of compiling such a knowledge base is get picked up by the community. And starting from 20 years ago, more than 300 geoscientists have spent more than 8 continuous human years to compile a knowledge base called PaleoDB. And this database contains more than 50,000 references, and this project is also highly successful and lead to more than 200 papers, and many of which published in Nature of Science. However, this effort of manually constructing a knowledge base has its own limitations. Take one of the largest databases of geoscience reference, for example. The number of references are growing in a rate like 100,000 references per year. If we compare this number with the total size of PaleoDB, we might see that it might take 16 continuous human years to just keep up to date with the growing rate of the current references. Although this estimate is pretty rough, it does show us how expensive and time-consuming that the Manual KBC could be. This huge amount of publications are not unique for geoscience, and every year there are more than millions of papers published in all fields of domain. Motivated by the sheer amount of data that we need to extract, one question that we really interested in over the last couple of years is, can we build a machine to read for us? As human beings, the word read means a lot of things to us. But for now, let's make that precise for the machine. By read, we mean that, can we build a machine that take as input resources like this, like journal articles, and automatically fill in a knowledge base stored as database relations? Motivated by this task, Deep Dive is a system we built to support this process and make that easier. Over the last couple of years, we have been building this type of system for a range of domains, and let me tell you more about them. One application we built is called Paleo Deep Dive. The goal is to extract paleobiological facts to build a higher coverage fossil record. The input of the system is a collection of journal articles, and the output is a knowledge base containing information about fossils. For example, if we see this sentence from journal articles, we expect the system to output a tuple to encode the fact that dinosaur T-Rex appears in the age Cretaceous. One of the most interesting aspects of Paleo Deep Dive is that it extracts information in exactly the same schema as PaleoDB, which is the manually constructed knowledge base that I just described. This enables us to compare the quality of Paleo Deep Dive with the professional volunteers who build PaleoDB. As we just mentioned, PaleoDB is an effort from 300 professional paleontologists who spent 8 continuous human years together. PaleoDB contains more than 50,000 documents, 100,000 fossil mentions, and more than 1 million relations. On the other hand, Paleo Deep Dive is a machine-created knowledge base that uses more than 2,000 machine cores and 46 machine years. It processes more than 300,000 journal articles and extracts 3 million fossil mentions and 2 million relations. We can aggregate both systems to get a biodiversity curve, and we can see that they correlate with each other in a really strong way. We actually conduct double-blind experiments to ask scientists to label the facts extracted in PaleoDB and Paleo Deep Dive on their correctness, and find that on the same relation, Paleo Deep Dive achieves equal and sometimes better precision as professional human volunteers. Deep Dive has been used to build similar systems across different domains. At the early ages of developing deep dive, we ourselves are the developer of KBC systems, and we get a lot of help from domain scientists. Some of these systems are actually getting pretty high quality. The Plato deep dive work that I just mentioned was featured in the news article in the July issue of Nature, and we are pretty excited about that. And according to the article, some of the geoscientists are pretty impressed by how high the quality our system can get. We also developed a system to extract information from the web, and it produced the highest score in a popular KBC competition among 18 teams. And now, KBC systems in deep dive are usually developed by domain experts other than us, including applications in the domain of pharmacogenomics and applied physics. To make these domain experts, who are not computer scientists, to actually use our system by themselves, deep dive models the whole process as a large inference problem. And the only thing we hope the user need to do is to keep providing features to the system without worrying about the algorithm that is actually running in deep dive. One of the common things of these applications is that at their early stage, many of them can only extract information from text and tables. And after we get high enough quality on these two types of information, one natural question to ask is, can we understand information buried in images in a deeper way? The reason that we are interested in the information buried in images is that it also contains hints to a lot of scientific questions. For example, if we could build a high-quality image recognition tool with deep dive, we could automatically classify fossils into different classes or orders. It could also help genomists to automatically identify phenotype of a given patient and use this information to get a personalized treatment. We talk about this with a lot of our scientific collaborators on what type of information they want us to extract from images. And one of the very first questions they often ask is, can you guys just run deep learning on my set of images and classify them? At first, we think, well, this requirement seems pretty easy because there are a lot of awesome tools that are available that we can just directly run them. But before we start the run, one question that we are facing is, on which machine should we run that? Should we run those tools on a larger amount of CPUs, or should we run those tools on a larger amount of GPUs? This question sounds like an easy one, but the more deeply we look into this problem, we found that it's kind of a mix of information. For example, on some of those tools, it's not uncommon for the system to run like 10x faster on GPU compared with CPU. But on the other hand, in industry, there are a lot of systems that are successfully built on a CPU cluster. Also, users have access to a different type of resources. Some of them might have access to a GPU cluster, some of them might have a CPU cluster, and some of them might just have some credit on the cloud. And some cloud has a GPU like Amazon's EC2, and some cloud don't have the GPU instance like Microsoft and Google. Given all this mixed bag of information, we decided to look deeply into this question. And where we start is try to investigate the difference between CPU and GPU in terms of running deep learning workload. Because if we compare a CPU and a GPU that are available on the cloud provided by Amazon, we can see that the difference between the amount of floating point operation they can do in a second is not that different. Therefore, one natural question that we ask is, because there's no terrible gap on the peak flops, can we achieve this peak? Or is there anything special in CPU that prevents us from achieving this? To study this question, we built a very simple prototype system called Caffe control. And we designed Caffe control to be a prototype system that takes the same input as a popular deep learning framework called Caffe and produce the same output. We found that the performance of CPU could be optimized such that we get near 80% of peak of floating point operations that can be provided by CPU. If we measure the speed of of Caffe GPU performance as 1, we can see that on an instance provided by Amazon, the CPU implementation of Caffe is really 10 times slower. And if you run Caffe control on the same instance, we can see that it's like 5 times faster than Caffe's implementation. It is still slower than GPU, but it's much faster on the CPU. Actually, when we add one more CPU to the machine, we get more than 10x speed up on CPU, and these two 8-core Haswell CPU can match the speed of a single GPU available on Amazon's cloud. But a more interesting result is that under our implementation, the difference of running deep learning over CPU and GPU is proportional to the number of floating point operations that a device could provide. This provides us a very simple rule of thumb for us to guide our users when they ask what type of devices they need. Also, because CPU is not that slow compared with GPU, it makes more sense to ask the question of how to run deep learning over a machine that has both CPUs and GPUs. And we are currently studying this question. Presently, how to achieve this speed up is actually pretty simple. We have a 4-page workshop paper to discuss 4 very simple techniques. And let me tell you one of them. Suppose we have 3 CPU cores and 3 images in a single batch that we can process in parallel. There are 2 strategies that we can do. We can either allocate all the cores to ask them to process a single image in parallel, and after they finish the processing, we ask them to move on to the next image and then the third image. This is the strategy that is currently implemented inside Caffe. But there are another strategy. That is, we can allocate a single image to a single core and ask them to process the whole, to process each images in parallel without any coordination. Which strategy will work better actually depends on the size of images and the size of CPU cache available on each core. And we found that if the amount of data is too small for each core, this process is actually not CPU bound. And that is one of the reasons some of the CPU implementation inside Caffe cannot get a peak floating point operation per second over CPU. And for a popular neural network called AlexNet, we found that over Haswell CPUs, the second strategy could be 3 to 4 times faster than the first strategy. Recall that one of our motivation is to build Caffe control is to help our users of deep dive to process their images. Now we have a prototype implementation to run deep learning. How are we going to use it for knowledge-based construction? The answer to this question is still under exploration, and I will tell you more about a very preliminary application that we are currently building. One interesting direction that we're exploring is how to combine deep learning with deep dive. If we are able to run deep learning efficiently, how can it help deep dive and our scientific collaborators? One observation is that many state-of-the-art image processing methods often requires a corpus with human labels. However, images without a human label can also contain valuable information. Take this page of paleontology journal article, for example. Although there are no labels for each image, but we can see the name of the fossils actually appears in the same document. Therefore, one question that we are interested in is, can we learn from these images without human labels, but has rich information surrounding them? More concretely, can we build a system that automatically reads a paleontology textbook and tells the difference between different classes of fossils, like sponges and shells? If such a system is possible, the input would be a set of journal articles, and the output would be a classifier that can distinguish between different classes of fossils. Our hypothesis is that we could extend the idea of a classic technique called distance supervision for text processing to automatically generate labels for image recognition tasks. To study this hypothesis, we have built a very simple prototype that uses deep dive to extract information between figure numbers and figure fossils appearing in the text and captions. And we use it to label figures as training example. And we then train convolutional neural network on the decently generated labels. Some early results shows that we can achieve pretty high quality on this very simple task. This result is still very preliminary, but we hope to explore further in similar directions to understand what framework that we need to build to support such a similar workload. Thank you for all of your attentions. Both the systems that I talk about today can be downloaded from their website. And we are actually working on understanding how to fuse these two systems together to support applications that require inference across text and images. Yeah, I think I still have like 4 minutes left. I can answer whatever question that you have. Yeah, if there's any questions. Okay. Thank you.